So we've used the disk method to find the volume of, say, a vase, which is basically treating it as if it's a solid. So the disk method will be finding the volume of the area inside, right? All that air and the glass and everything. But what if I just want the volume of the glass? I mean, to be real, this has a big hole in the middle, right? And if I want the volume of that glass, the disk method won't work exactly because the disk assumes a circle going straight across, right? So you cut into it crosswise and you're going to have a circle. But what if I want to find the volume of that glass alone? Well, for that, we would use the washer method. The washer method assumes that you have a cavernous hole inside, right? Which is actually more realistic for the sake of, oh, I don't know, vases or pottery, that kind of thing. Because of course it's not solid. So if you want to know the volume of the pottery, but you don't want to know the volume of the air inside, right? The disk method will find the volume of the air inside because it treats it as if it's solid, or if it's a solid object. But if it's an object with a hole in it, then you'd want to use the washer method. And you can see the different visuals here. It's sort of like an apple with a core taken out of it, right? So you have this bit drilled out of the center. What's the volume of the material on the outside? So you're going to cut across it just like you did with the disk method. It's just that you're going to have to take away the part that's not there. So if you see here, you take this little, well, rectangle, and then you rotate it around, right? So as it rotates, that little rectangle forms, well, I want to say it's not quite a disc, it forms a washer, right? It forms this kind of outer circle and an inner circle, and then the material between the two, right? It's a washer. And just to be clear, I mean this kind of washer, the kind that you have in a toolkit. Those are called washers, right? You use them with screws, right? So those are what we're talking about. Those are what we're looking at. And we want to be able to stack them up inside of our object and form that object, right? It's not like a washing machine washer. So it's a washer as in terms of a circular disc that has a hole taken out of it, okay? All right, so let's think about that rectangle and what it means. So the washer method essentially is the disk method. It's the disk method more fancy, right? So it's the disk method with a piece taken out of the center of it, okay? So we imagine a stack of, now washers is one thing. I'm old, so I can also imagine a stack of these bad boys, DVDs, right? So if you have a stack of DVDs, they have a hole taken out of the center, right? So, but I could find the volume of the DVD portion, right? You can see my camera right there. There it is. All right, so imagine a stack of DVDs or washers. Depending on if you feel like being audio visual or if you feel like, being a tool, right? Using your toolkit. So if you want tools, then think of washers. If you want your audio visual equipment, think of DVDs, right? So if the solid of revolution has a concentric hole in it, then you'll use a modified version of the disk method, right? This is the disk method. It's just a little bit modified, and it's called the washer method. So the washer method and disk method are very similar. Sorry, I'm stacking my DVDs back up. So the washer method and disk method are the same. The concentric hole, what that means is the hole is taking place around the axis of rotation. So if you think of my jar yet again, right, the axis of rotation is in the middle and the hole is also rotational around that, right? That's all that means, right? Concentric meaning it's around the axis of rotation. It's not a hole, taking place someplace else like Swiss cheese, right? It's a hole that's around your axis of rotation. That's what that means. Okay, so then we would graph the function over the given domain and range. We would find and label our axis of rotation, just like the disk method. Now the thing about the the function in the domain and range, you'll spot that you have to use the washer method. I'm going to sneak down here real quick because the washer method will have a gap between the axis of rotation. So you can see the axis of rotations right here or right here. And you can see there's a gap, right? The region does not touch that axis of rotation. That's a sign that you have to use the washer method. Matter of fact, I'll make a little note. Use the washer method when the region does not touch the axis of rotation. When it does touch the axis of rotation, then you can use the disk method. All right, we draw an approximating rectangle, but as with the disk method, it's always perpendicular to the axis of rotation. Just like the disk method. Right? Again, this is the disk method. It's just modified. The thickness of the disk will be labeled dx or dy. The radius of rotation. Now, this is where it's different. It's the outer radius squared minus the inner radius squared. That's the modification from the disk method right there. All right, so what's that going to mean? Well, let's look at it. So we have a horizontal axis of rotation on this particular one. You can see from a mile away, hopefully, that your thickness is dx when you have a horizontal axis of rotation, just like it was when you had disk method. It's the same thing. Over here on this side, the thickness is dy, right? And your axis of rotation is vertical. Okay, now here's the trick. You can't deal with just r of x. You have to modify it. So you need to find that length of that piece of the rectangle right there. Now the length of the rectangle is tricky, right? That's what we're trying to figure out, that radius. That radius will be the length of this rectangle. Right? That will be your radius of rotation. Sorry, I couldn't fit the word rotation in there. Now, how do we find it? Well, you take this outer function. This is an outer function. And you say, okay, this whole thing from there to there is capital R of x. And then this little piece from here to here is little r of x. And so then what you do is you say, okay, I'm going to take the capital R of x because that's the outer, and then the little r of x is the inner. Those are both functions in x. And then you square each one of them. So you take capital R of x and then little r of x. And then you square each one of them. So you take this one squared minus this one squared. You're basically finding the area of the big circle and then minus the area of the little circle. So if you think of a DVD, what you're doing is finding the area, because you're going to multiply by pi, right? So it's pi r squared. So find the area of the big circle, and it's the area of the whole, and you'll have it, right? So little r of x will get you the area of the whole, big R of x will get you the area of the outer circle. And then together, once you subtract them, you'll have found the area of the disc, well, the DVD itself, the washer itself. Same thing over here, right? So this length of this piece right here, that is your radius of rotation. Well, I'll be able to fit it in on the side. Radius of rotation. Now what that means is that now this is a function in y, right? So you have this same curve, but you're rotating it a different way. So you think of it as this is r of y. And then this piece right here is little r of y. So you take capital R of y and you square it, minus little r of y, and you square it. And that's the washer method. The hard part, honestly, is finding these two functions, figuring out which way you want to go, and then finding the correct functions for little r of y and capital R of y, or little r of x and capital R of x. If you can get those, then it's pretty much the same as it was with the disk method.